All right, let's go to misconception question number 2. And in this question, we have a football kicker who's kicking 3 different kicks that all take a different parabolic path, right? But they all reach the same height. And the question is, which of the 3 kicks is in the air for the longest time if they all reach the same maximum height? Okay? All right, so I'm going to start here. All right, I'm going to start by writing our kinematic equation of V2 equals V1 plus AT. And I like this equation, okay, because of a couple of things. One is that it has T, and the other is that it has A, okay? So it's the simplest formula that has both T and A in it, okay? And I want A because that's one thing that I know for sure. I know that this is gravity that's acting on this ball, right? And I want T because I'm looking for time, right? Which of the 3 kicks is in the air for the longest time? So I'm solving for T, right? And I want to be specific, like the A that I know is the A in the Y dimension, right? So I got to put little subscripts of Y for all of these to remind myself that I'm dealing with just Y, okay? And so if I solve this equation for T, what do I get? Well, I get V2Y minus V1Y over A equals T, right? Over negative 9.8, essentially, right? Does that make sense? Right? So then that means that my T is just going to be V2Y. We know that the Y component at the peak always has to be what? 0, right? So this is going to be 0 minus V1Y over negative 9.8, right? Okay, so because there's a 0 here, I can basically just go ahead and get rid of this guy, right? He doesn't really exist. So it's just a negative V1Y and a negative 9.8, and they both become positive, right? But here's the thing. If these guys all go to the same height, the only thing that determines how high it goes is the speed that you kick it in the Y direction, right? Whatever that speed is in the Y direction that you're kicking it determines how high it goes. You have a low velocity, it goes low. You have a high velocity, it goes high, right? So if the fact that these are all the same height means that for each kick, this V1Y is the same. And if this V1Y is the same and 9.8 is the same for every kick, it also means the time must be the same. So this, my friends, is a trick question, okay? The answer is actually that there is none that have the longest time. They all have the same time, okay? All right. I will now move on to a projectile motion problem with a steady stream. So everything that we've done so far has involved a single particle, right? Either a football or a human cannonball or et cetera, right? Now, what happens in the case when you have a steady stream? Does anything ever change, right? Like for the example of a power or a fire hose, right? Turns out, no. It's the same exact problem. So you just do what we've been doing all along. And I almost am tempted to say, pause it and do this problem on your own. In fact, actually, I do recommend that. Pause it, do it on your own and see how it goes and then come back to us. But if you'd like to work it with us together, let's do it. So we have this fire hose that's held near the ground at some angle theta. It shoots water at a speed of 6.5 meters per second. At what angle or angles should the nozzle point in order for the water to land 2.5 meters away? Why are there 2 different angles? And we want to sketch the 2 trajectories. Okay, so let's start by showing you this, okay? We've talked a little bit about how the maximum possible range is at 45 degrees, right? So at 45 degrees, then any object goes as far as it can possibly go, okay? Now, if I were to, let's say, do 30 degrees, right? So let's do 30 degrees instead. I'm not going to go as high. I'm not going to go as far, right? But if I do 60 degrees, I'm not going to go as far either, but I land in exactly the same spot as 30 degrees. So whenever there's this symmetry here, where this angle here equals this angle here. So if this is 60 degrees, then that's 30 away from the 90 degree, right? So whenever there's that symmetry, you get the object landing in the same spot. So it would be the same thing if this was like, let's say 15 degrees. Okay, so let's say that that's 15 degrees. That if I did another shot here that was 15 degrees away from the y-axis, I get the same sort of thing. And obviously these would have to be totally symmetric. I'm not drawing them perfectly symmetrically, but I'm not a good drawer, and that's just the way it goes. Okay, so but if that's 15 and that's 15, we still have the symmetric. It's going to land at the same spot. So that answers the last question. Why should we get two different angles? Okay, but now to actually find out what those angles should be, let's do a laundry list. And how many? Two. All right, so first we're going to start out with our x laundry list, and then we're going to start out with our y laundry list, right? So we have v1y, v2y, ay, dy, and t, right? That's everything, I think. Then we have, oh, these should be x's, 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 okay? And this is going to be v1y, v2y, ay, dy, and t. So let me just make these a little bit more clear. This should be an x, this should be an x, this should be an x, this should be an x. Okay, and t is going to be the same for both dimensions, right? All right, lovely. So let's start filling stuff in. We know that the x component should be the actual speed of the water, which they say is 6.5 meters per second here. So that's going to be 6.5 cosine of theta naught, the angle that we're looking at. And you guys by now know that this guy over here is going to be the same, 6.5 cosine theta naught, right? A is 0, right? And d is the distance away that it lands, which they say is 2.5. Man, we got everything we need there. We don't have the time, but as you guys know, it's usually the first thing that we calculate. Okay, what's going on in the y dimension? Well, instead of the cosine of the angle, y gets the sine. So we have 6.5 sine of theta 0. v2y should be, well, it's going all the way up and then all the way down, right? And so it starts and lands in the same spot, which in this case, remember we said it's going to be symmetric but negative, right? This a, the acceleration is obviously negative 9.8, right? And the dy, it starts and ends at the same height, so that's 0. All right, we got a lot here to work with, guys, right? So as I always suggest, I recommend before you do anything, solve for time, right? I am going to use this dimension over here to solve for time. And what do I know? Well, I know that v2 equals v1 plus at, right? And I'll put little y's there to show that I'm doing this in the y direction, right? So that means that I have negative 6.5 sine of theta equals 6.5 sine of theta plus, minus 9.8 t, right? So this acceleration is negative, obviously, so I have to put that negative sign there, okay? And now I'm going to bring this guy over to the other side, and I get negative 13 sine of theta equals, well, I'll just go ahead and divide also by the negative 9.8, and I get t, okay? How's that? These cancel, these become positive. So now I have the time, and I could put 13 sine theta over here divided by 9.8. Okay? All right. So now I can use this dimension to solve, hopefully, for my theta, right? Because I also know, and I'm going to erase this chunk now so that I have more room. Okay? I also know that dx equals v1x t plus 1/2 ax t squared, right? And we know that in an x dimension, ax is 0. That goes away, right? And that leaves us with 2.5 meters over here equals v1x, which is a 6.5 cosine theta, okay, times 13 sine theta, and this is all over the 9.8. Okay? All right. Now, this is a little different than what you're used to. Okay? There's a couple things you can do here. First, and what I recommend the most doing is multiplying both sides by 9.8. Okay? Dividing by 6.5, dividing by 13, right? And you end up getting a cosine theta times a sine theta. Okay? Now, the shortcut is you can just put this in any equation solver. It's not like a normal, just plain old inverse tan, right? It's a little bit trickier. So you can put this into an equation solver either in your TI calculator or in just like any kind of equation solver that you Google online. Put in the equation cosine theta times sine theta equals whatever you get here, okay? Cosine theta times sine theta has a trig identity, which makes it easier to solve the problem. I encourage you to do either method, but when I did this, I ended up getting thetas of 18.1 degrees and 71.8 degrees. Okay? Does that make sense? Is that symmetric? It is. 18.1 degrees is the same distance from 0 as 71.8 degrees is from 90. So you get this effect where it's going to land in the same exact spot. Okay? So go ahead, check my answer on that. Make sure I'm kosher. And for now, I want to pause there and let you guys explore, understand, make sure it makes sense to you. If you have questions, reach out to me. In the last video, we will be talking about how to find the gravity on the moon simply from your golf stroke. All right, see you there.